Okay, now we're recording. All right. So again, the law of conservation of mechanical energy is right here. This is a very important concept. And what you're doing is you're looking at the potential energy and kinetic energy of one scenario compared to another scenario, or initial versus final. That could work too. So a toy gun uses a spring to shoot plastic balls of that mass. The spring is compressed by 3 centimeters. Let K, looks like K is some, oh, this is doing springs. We're not gonna do springs. So let's forget about that one. So let's actually look at one of these problems down here then. Let's look at maybe number 10 might be a good one. Let's see. That's highest points. Okay. So just trying to think carefully about this problem here. Okay. So actually, yeah, I think we'll be fine with 10. So here's the deal with number 10. So you have a water skier, and he's jumping a ramp at 14 meters per second. However, there is an angle here that we must consider. So our initial velocity is that. There's initial velocity in the x direction and initial velocity in the y direction. And they're pointing in that fashion. Now, when you're here, you're at the peak, right? At the highest point. So let me ask this question here. This guy's velocity at its peak, is it all vertical, is it all horizontal, or is it a mixture of both? So Isaac, what do you think about this one? So when we're at the peak, the velocity of the water skier, is it all vertical, is it all horizontal, or is it all, or is it a mix of both?
It's vertical.
Well, his velocity is going to be all horizontal, though. So the vertical velocity at this point is actually 0.
Oh, yeah.
Right. And it's going to be 100% horizontal. So this right here is actually going to be Vx. And Vx is actually going to be constant throughout the whole scenario, because your acceleration is only going to be acting in the downward direction. Remember, your acceleration due to gravity is going to be negative 9.8. So what we know now is that if this is 14 and this is 13, we can actually get the initial velocity in the y direction. So I'll call on someone else. So Jonathan, looking at this right triangle here, how do I get the initial velocity in the y direction? What famous theorem do we know?
What was the last?
That involves right triangles.
Wait, what did you say before that?
Yeah. So how am I going to find v0y if it's the length of that leg on the right triangle?
By doing SOHCAHTOA?
Well, no, because we don't know the angles.
Oh.
So what theorem do we have that involves all the sides of a right triangle? What is that called?
Oh, I know what it is, but I just forgot the name of it. It's
Pythagorean theorem.
There we go. Yes.
Okay.
That.
So you use a squared plus b squared equals c squared. So you're going to do 13 squared plus b squared equals 14 squared. If you work it out in a calculator, you get 196 minus 169, which should be, 28, I think. So v0y is going to be root 28.
27.
Was it 27? You're right. You're 100% correct. Thank you. Or 3 root 3, if you reduce it. Thank you for catching that. So that's going to be the initial velocity in the y direction. So what we can gather is that now we have to use conservation of energy, basically. That's what we're trying to do here. So our kinetic energy initially plus our potential energy initially is going to equal our potential energy final, or our kinetic energy final, let me draw a little better. Now, remember, kinetic energy is 1/2 mv squared, but because we're focusing on the vertical, we're going to use the v0y. So right below it, we'll do in blue, 1/2, and I don't know the mass, but don't worry because it's actually going to cancel. So I'll just put 1/2 times mass times the velocity, which is going to be 3√3 squared. The potential is going to be mgh. It's going to be m times 9.8, and actually it's going to be negative, mind you, but we're going to keep it all positive because the distance is going to be negative as well, times its displacement, which I don't know. So I'll call it hi for now. The kinetic energy, finally, because you have zero kinetic energy, there's no motion. Your motion is for a brief moment. Plus m times 9.8 times the final height. Okay. So if we think
the heights from, like where's the h? Where the h is from?
So h. It's a great question. So hi is going to be right here. So here's the water. That's going to be hi. HF is going to be right there.
But why are you putting it into that blue equation? Because I don't see how you get that from like.
So the right before the skier jumps off, the skier has kinetic energy, which is 1/2 mv squared, and we have the velocity in the y direction there. But the skier also has potential energy too, because the skier could just fall straight down as well, and that's mgh. And so the height of the skier right before he leaves the top of the ramp is hi. I'm just calling it hi, the initial height of the skier. Does that make sense?
Yes, it does. Thank you.
Yeah. And then we reach the top, I'm going to call it HF. What do they want, though? They want the height above the top of the ramp. So capital H is actually going to be HF minus HI. So I should be able to get this pretty easily now. So I have 1/2 times m times 27 plus 9.8 m times HI equals 9.8 m times HF. Now, fortunately, all the m's cancel. That's why you don't need to know m. Every term has m, they cancel out. And if you move things around, you get 1/2 times 27 equals 9.8 HF minus HI. Because you move the 9.8 HI to the other side and factor out the 9.8. So then you get, let me erase stuff here. Then you get 13.5 equals 9.8 times capital H. Remember, capital H was the difference between the final height and the initial height. And so you're just doing 13.5 over 9.8, which should get us pretty close to 1.4. So that is a great example of using some of the stuff we learned last week with like breaking components down, like with vectors, like you have your velocity, understanding that you have to use a vertical velocity because the acceleration is working in that fashion. So you're not working with the horizontal velocity because the acceleration is, so it's all about our range of motion, and we're really just curious about the vertical motion. So which is why we're looking at energy in that fashion. And of course, you have no kinetic energy at the top. and you're using the conservation of energy as well. So that's a great example. And that's something I probably put on our test this week, something kind of like 10. I really like that problem a lot because it's not too bad. It uses some old stuff, but it really forces you to use the conservation of energy and be kind of mindful of what the question wants. It wants the difference in height. And of course, the m's cancel. You didn't need mass at all for that one.
Wait.
So that's good.
I'm confused on how there's 3 M's, yet they still kind of cancel.
Yeah, so if you think about it, on the left side here, you can pull the m out, right?
Oh, I see.
So it's half times 27 plus 9.8 hi. And then on the other side, you have 9.8 m hf. So the m is not being multiplied to that junk on the left side, and m is being multiplied to 9.8 hf on the right side. So you divide out m, that's what happens. You can only do it when every term has it, though, mind you. You can't just be, cherry picking about it. Like, you have to really make sure every term has the m. So that's why the math was not necessary for this problem. We did not need to know it at all. So that's one example of doing stuff here. So I'll have you guys try, I think, maybe doing 2 problems. And then we'll do a bit more when we come back. So, but let's do actually let's make it 3 problems. So I'm going to go and clear the drawings, and let me stop the recording.